Welcome to this next video in the playlist on real analysis. This video is entitled the Bolzano-Weierstrass theorem. Now the objective for this video is to prove that all Cauchy sequences in the real numbers converge to a limit. That theorem is not actually the Bolzano-Weierstrass theorem. The Bolzano-Weierstrass theorem we are going to use to prove that. They're very much so related. The Bolzano-Weierstrass theorem, as we'll see, is the theorem that all bounded sequences within the real numbers have a convergent subsequence. However, from that, it very quickly then follows that all Cauchy sequences must converge. So they're very much so related, and the Bolzano-Weierstrass theorem has a fancier title that makes a good video title, hence why we've called the video that. But the main objective is to prove that all Cauchy sequences converge within the real numbers, to prove that the least upper bound property implies that that is true. So hopefully all my viewers are familiar with the concept of a sequence and the concept of the limit of a sequence. So let's just go over the notation, just as an introduction. This is the notation we're going to be using for a sequence. So a sequence formally is a function from the natural numbers to your number system of interest, and your number system of interest could be the rationals or the reals, the two ordered fields that we've studied so far in this playlist. And you're going to have the terms of the sequence, and we often write these like so. So the first term of the sequence, the second term of the sequence, the third term of the sequence, and it goes on, of course. And this is how you can view it as a function from the natural numbers to your number system, because 1's being mapped to this, 2 is being mapped to this, 3 is being mapped to this, and so on. And we'll denote the nth term of the sequence xn, and we can also use this notation to denote the sequence generally. The concept then of the limit of a sequence, and this concept works both in the rational numbers and the real numbers. The concept of the sequence getting closer and closer and closer to a limit is that the sequence is getting indefinitely close to that point within your number system. So formally, the way you define this is that for all epsilon greater than 0, there must be a big N, a point in the sequence that's in the natural numbers, such that for all little n greater than or equal to big N, so for all the points of the sequence beyond that big N, it must be the case that the absolute value of xn minus the limit, which is, if you like, the distance, how far away that point is from the limit, must be less than epsilon. Now, we haven't formally defined what is meant by the absolute value, but you should be familiar with that function from elementary maths. You can define that both in the rational numbers and the real numbers, where if the number is greater than 0, the absolute value is just equal to that number, and if the value that you want to take the absolute value of is less than 0, then the value is going to be the additive inverse of that value. So pictorially, what this definition is saying is that if this sequence converges to some limit L, so we've got our picture of the real line here, and let's say it's going to converge to this limit L, then what needs to happen is that no matter what epsilon you pick, you must be able to find a big N, a point in the sequence, such that that point and all the points afterwards are within that epsilon interval around the point L. So you must be able to find a point in the sequence where it and all the little red points afterwards are inside there. So really what this is saying is that the sequence must get and stay indefinitely close to your limit L in order for the sequence to be converging to that point L. And this definition of the convergence for a sequence works in both the ordered field of rational numbers and the ordered field of real numbers. Of course, in the rationals, the epsilons that you're going to be choosing are all going to be rational, whereas in the reals, you've got much more epsilons. All the non-irrational numbers you can also pick as epsilons. But this definition still works, and it still captures the intuitive notion of what it means for a sequence to converge to a limit L, i.e. that all the points are getting closer and closer and closer and closer to that limit L. Now, what we're really interested in this video is the concept of a Cauchy sequence and whether Cauchy sequences converge or not. So let's now look at the definition of a Cauchy sequence, named after the famous mathematician Cauchy. So a sequence xn is called Cauchy if, and this is now the property that it needs to obey, and let's dissect this down. So for all the epsilon greater than 0, once again, there must exist a big N is an element of the natural numbers, so there must exist a point in the sequence such that if you take any two points in the sequence beyond that big N, so you pick a little n and a little m that are beyond that big N, so somewhere up here, and you look at how far away they are from one another, so you take the absolute value of xn, the little nth term of the sequence, minus the little nth term of the sequence, and you look at how far away they are from one another, that must be less than epsilon. So what this is saying is no matter how small you make 0, so you can make it indefinitely small, there must be a point in the sequence where all of the terms after that point in the sequence are that close to one another. So this definition is saying that the points of the sequence must get and stay indefinitely close to one another, because you can make that epsilon as small as you like. So however small you make it, you can find a point past which all of the points of that sequence are that close to one another. So intuitively, these should be sequences that do converge, because how can they possibly not? If they're getting indefinitely close, the points of the sequence, to one another, how can they possibly not be converging to some sort of limit? This is what motivated Cauchy to come up with this definition, because he thought these sequences surely must be ones that converge. Now, the problem is, if you go to the rational numbers, you could have sequences of rational numbers that are Cauchy, they're getting indefinitely close to one another. However, they are converging to a gap in the rational numbers. Remember, we've discussed this problem with the rational numbers. Square root of 2, for instance, is not in the rational numbers. There is no number that squares to give 2 in the rational numbers. It's a whole in the rational numbers. So you could create a sequence that should be converging, but doesn't have a limit in your number system, because the thing that it's converging to is a gap in your number system. And we created the real numbers so that it wouldn't have those gaps. And what we're going to see is that from the least upper bound property, it follows that all Cauchy sequences do have a limit in the real numbers, because they do all converge down to something, and there are no gaps in the real numbers, so they do all converge to something that's actually in our number system. Just to absolutely convince you of this point, I want to take a sequence within the rational number system, so a sequence of rationals that is going to obey the criterion to be Cauchy, so it's going to be a Cauchy sequence of rationals. However, it's not going to be a convergent sequence. It's not going to converge to a limit. And the reason it's not going to converge to a limit is it's going to converge to a whole in the rational numbers. It's going to converge to the square root of 2. So I'm just going to show you how I can really easily do that. So we've got our real line here, but of course we're only going to be using rational numbers for our sequence. We've got the square root of 2, which we know is within the real line, but obviously isn't in the rationals, but that doesn't matter because we're not going to actually use the square root of 2 in our sequence. So the first two terms of the sequence we're going to take are 0 and 2. Why? Because they're either side of root 2. So we'll take 0 and 2 as the first two terms of our sequence. And then this is how we're going to proceed to get the next terms of the sequence. So we're going to divide our interval between 0 and 2 into 2 down the middle. So the middle is at 1, so we've divided it now into 2 halves. And we then look at which of these halves contains root 2. How do we work that out? Well, we just look at 1, and what is 1 squared? It's equal to 1, which is less than 2. So 1 is squaring to something less than 2, and that then implies, by arguments that we've seen in previous videos, that 1 is therefore less than the square root of 2. So we want, therefore, to consider the interval from 1 to 2, because that's going to be the interval that still contains root 2. So we put 1 as the next term of the sequence, and now we're interested in the interval from 1 to 2, and we want to divide that in 2 again. So we take the point halfway in between, which is 1.5. That's going to be the next point in our sequence. And again, we want to consider of those two intervals, so from 1 to 1.5 and from 1.5 to 2, which of those two intervals contains root 2? Clearly, it's the interval from 1 to 1.5. And the reason for that, again, is that 1.5 squared is greater than 2, which then implies that 1.5 is greater than the square root of 2, again by logic that we've used in previous videos. So we then look at this interval from 1 to 1.5, and we'll then transect that into, which of course is 1.25, so that will become the next point in our sequence, and we go on like this, getting a narrower and narrower interval that is always going to contain the square root of 2. So for the next term, the interval that still contains the square root of 2 is going to be from 1.25 to 1.5, rather than from 1 to 1.25, and then halfway between that is 1.375, so you'll go on and on like this, and you can see that all the terms of this sequence are going to be rational numbers. None of them are going to be outside of the rational numbers. Hopefully you can also appreciate that this sequence is going to be Cauchy because all the terms of the sequence are going to be in whichever interval we've got to. So the way we're making this sequence, we're getting a smaller and smaller interval that is interesting to us. And all the terms that are going to come up indefinitely in the sequence are always going to be in that little interval. So they're always going to be maximum distance from one another, the length of that interval. And that interval is halving each time we do this iterative process. Therefore, it's going to get indefinitely small. So however small you want to make epsilon, I can find you a point in this process where the interval that we've got to by that point is going to be smaller than that epsilon, and therefore all the points beyond that in the sequence are going to be within that distance of one another. So it is going to obey this Cauchy definition. The points of this sequence are getting and staying indefinitely close to one another. Now, quite clearly in the real numbers, this sequence is converging to the square root of 2, and the reason that you can see that is the way we define this sequence involved this ever-decreasing size interval that always contains the square root of 2, and whichever point you've got up to in the sequence, which pertains to that interval that you're at the moment, we know that all the points beyond that in the sequence are going to be inside that little interval. And we're making that interval indefinitely small in the process of creating this sequence, and therefore, hopefully it's obvious to you now that the points of this sequence are going to get and stay indefinitely close to the square root of 2, which is ultimately all that this jargon here is actually saying. So hopefully it's obvious to you that this sequence is going to converge to the square root of 2 in the real numbers. Now that means it can't be converging to something in the rationals, because suppose it was converging to a limit that's in the rationals, then it would be getting and staying indefinitely close to that limit. Now come across to the real numbers, bring this sequence across into the real numbers, it's still going to be getting indefinitely close to and staying indefinitely close to that member of the rational numbers that is still an element of the real numbers. But we've shown that we understand that this is converging to root 2, so it can't be converging to two separate limits in the real numbers. This definition doesn't allow that. It can't be getting and staying indefinitely close to two different elements of the real line. So that's the reason it can't converge to something in the rationals. It's converging to root 2 in the reals, ergo it's non-convergent in the rational numbers. So we have a Cauchy sequence that is not convergent in the rational numbers. So this theorem that all Cauchy sequences converge to a limit doesn't hold true in the rational numbers. It's something that requires there to be no holes. It requires the least upper bound axiom. So the goal for the remainder of this video is to prove that all Cauchy sequences converge to a limit within the real numbers. In order to do that, we're going to prove the Bolzano-Weierstrass theorem. And in order to prove the Bolzano-Weierstrass theorem, we firstly need to discuss a theorem about monotonically increasing and monotonically decreasing sequences within the real numbers. Now, this theorem doesn't have a fancy name, but it's very important and also very simple. So let's do it now. So firstly, let's discuss what is meant by a monotonically increasing sequence. So really simple, this is just a sequence that gets bigger and bigger and bigger. So every term is bigger or equal to the last term. So this is quite simply the definition that the next term along, xn plus 1, is greater than or equal to xn, and that is true for all n. So if we put in little n is equal to 1 here, we get that x2 is greater than or equal to x1. If we put in little n is equal to 2 here, we get x3 is greater than or equal to x2. So all of this, on and on, x4 has to be greater than or equal to x3, x5 has to be greater than or equal to x4, etc. All of it has to be true. It has to just get bigger and bigger and bigger. It never goes backwards. So at no point is it true that the next term along is smaller than the term we're on at the moment. That's what is meant by monotonically increasing sequence. And hopefully you can then work out what is meant by monotonically decreasing sequence. It's the other way round, where it just gets smaller and smaller and smaller. The next term along is always less than or equal to the term that you're on at the moment. So an example of a monotonically increasing sequence would be the sequence 1, 2, 3, 4, 5, 6, 7, 8, etc. That's not a particularly interesting monotonically increasing sequence. In fact, the theorem that we're about to discuss requires another thing to be true about the monotonically increasing sequence. Namely, it requires it to be bounded above. Monotonically increasing sequences that are bounded above are interesting in the real numbers. In particular, they have a limit. They converge to something, and that's what we're about to show. So let's just discuss what bounded above means. So this means that there is an upper bound, that there is an element in our number system, in the real numbers, that is greater than or equal to all the elements of your set. So a sequence can be viewed as a set. You can collect all of the terms of the sequence together and make a set, and then you can talk about that set being bounded above. So for the sequence to be bounded above, this is what it means, that all the terms of the sequence x little n must be less than or equal to some big B, which is going to be an upper bound for the sequence, and that needs to be true for all little n is greater than, is an element of the natural numbers. So on our picture here, we've got the real line, and we've got an imaginary monotonically increasing sequence here. So this is the first term, this is the second term, third term, fourth term, etc. And they're all getting closer and closer and closer and closer here, and sort of accumulating up at this sort of accumulation point here. And then we have this big B here that is an example, and we could have picked another one. We could have picked here or here. There's nothing special about this one, but this will do. This is an example of an upper bound for our sequence, because clearly every single element of the sequence is less than or equal to this big B. So the theorem is that if you have a monotonically increasing sequence that is bounded above, that it must converge to a limit. And intuitively, the reason this is true is if you have a monotonically increasing sequence that is not bounded above, such as that example that we've given before, 1, 2, 3, 4, 5, or you could have had 2, 4, 6, 8, 10, etc., those are not bounded above, and you can see that they clearly do not have a limit. They just go on and on and on and off. They diverge. But if you have an upper bound, then you've bounded this, you've restricted it hugely, and somehow you've got to now fit in an infinite number of points of this sequence into this bounded finite little space here. And the only way that can happen is for them to start getting closer and closer to one another, accumulating up, because remember, they can't go backwards. They have to always get higher and higher. But the only way that they can't cross this upper bound is for them to start accumulating up to a point that is going to then be the limit. Now let's just prove that this is the case, that they must have a limit. So here's how we show that. So again, let's put all of the elements of the sequence into a set. So let's take the set of all elements of the sequence, so all x little n, where n is an element of the natural numbers. And then let's consider taking the least upper bound of that set, the supremum of that set. And because we're in the real numbers, and here's where we're using the least upper bound property, that least upper bound must exist, that supremum must exist. And this is where this fails in the rational numbers, that these points will still have to accumulate, this infinite number of points will have to accumulate somewhere if there is an upper bound to the sequence. However, it might be accumulating up on a hole within the rational numbers. But in the real numbers, there are no holes, so the supremum must exist. We'll call that L, the least upper bound. And now let me convince you that L is going to be a limit for the sequence. Well, to show that it's a limit for this monotonically increasing sequence, we just need to show that it gets and stays indefinitely close to L. So for all epsilon, we must be able to find a point within the sequence where from that point on, all the points are within that epsilon distance of L. So just create an epsilon ball around L, an epsilon interval around L, and we now need to show that we can find a point in the sequence where all the terms from that point onwards are inside that epsilon interval. Well, because L is a least upper bound for this set, there must exist an element inside that epsilon ball. The reason for that is that if you consider the point L minus epsilon, which I've drawn on the picture here, if L is a least upper bound, then L minus epsilon cannot be an upper bound, because if it was, it would contradict L being the least upper bound, and therefore there must be a point within this set that is greater than L minus epsilon, i.e. there must be a red dot in here, greater than L minus epsilon. And then whatever that point of the sequence is that you found that's inside this epsilon interval, you can then use that as your big N, because all the other points of the sequence after that point, they have to be greater than or equal to that. We know they're all less than L because L is an upper bound for every element in the sequence. So they're all going to also be within this epsilon interval. So you've found a point in your sequence where from that point on, all the points are inside your epsilon interval, and you can do that for any epsilon. So clearly then this sequence is getting and staying indefinitely close to the least upper bound of the set of all the terms of the sequence. So that's how you prove then that if you have a monotonically increasing sequence in the real numbers that is bounded above, then it does have a limit. Now the same argument works for the thing going the opposite way. So if you have a monotonically decreasing sequence, so one getting progressively smaller, that is bounded below, again it has to accumulate up somewhere, and that accumulation point is going to be a limit, because in the real numbers there are no holes, so it can't be accumulating up to a hole. Of course, if it's not bounded below, then that of course doesn't limit it at all. It could be -1, -2, -3, -4, which quite clearly doesn't converge to a limit. But monotonic sequences that are bounded in the respective direction in which they're going do converge to a limit in the real numbers, because they have to accumulate up somewhere and they can't be accumulating up to a hole in the real numbers. So next we're going to move on to the Bolzano-Weierstrass theorem. Now in order to state the Bolzano-Weierstrass theorem, we must make sure that everyone understands what is meant by a subsequence. So to illustrate this, I've got some examples here. So let's start off with this original sequence, a very simple sequence. It's just the sequence 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., the natural numbers. An example of a subsequence of that is shown below. 2, 4, 20, 31, 49. So you pick some terms of the sequence to use, and you can omit others. So we've omitted the term 1, and we've then gone to the second term of the sequence, and we're going to make that our first term in our subsequence. We've then omitted the term number 3, and we've kept term number 4, and then we've omitted a whole bunch of terms, and then we've kept term number 20. So you can cancel out terms from your sequence and get rid of them to create this new subsequence. You must preserve order, however. The order of these terms in our new subsequence must be correct, i.e. this is the second term of our original sequence, this is the fourth term of our original sequence, this is the 20th term, 31st term, 49th term. They're still in the correct order. You cannot have something like this. This is not an example of a subsequence of this, because you've actually changed the order of the terms here. So we've got 3, 1, 7, 2. Here we've decided to put the third term of our original sequence here and then the first term here. That's not right. All you can do when you go from a sequence to a subsequence is cancel out terms, but you have to preserve the order of the ones that remain. You can't start switching them up. Here we've cancelled out 2 and we've actually swapped the order of 3 and 1. That's not allowed. That's not making a subsequence. Subsequence, you just get rid of a bunch of terms you don't like and leave the remaining ones, group them back together as though the other terms were never there, and now you've got your subsequence. So now let's state the theorem that the entire video is titled, the Bolzano-Weierstrass theorem. So the Bolzano-Weierstrass theorem is as follows. It's a theorem about the real numbers. Any bounded sequence within the real numbers has a convergent subsequence. Let me give you a wonderful example to illustrate this. So firstly, let's just talk about what is meant by bounded. So bounded means that it's both bounded above and bounded below. So there is a BU, an upper bound, and a BL, a lower bound, such that all the terms of the sequence are less than or equal to the upper bound, and all the terms of the sequence are greater than or equal to the lower bound. So they all have to be or lie within a interval, a bounded interval of the real numbers. If your sequence satisfies that property, and a whole bunch of sequences won't, some of them will go off up here and never have an upper bound, and some of them will go off down here and never have a lower bound, and some of them might do both. They might go off in both directions and not have either an upper bound or a lower bound. So it is a requirement for this theorem to work. It has to have both an upper and lower bounds. It has to be contained within a finite portion of the real line. If that is the case, then that sequence will have a subsequence that does converge. The sequence might not be convergent itself, but it will have a subsequence that does converge. Let's look at this example. So here we have a sequence 1, minus 1, 1, minus 1, 1, minus 1, and it goes on and on like this. So just flitting between here, 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 here for all eternity. That is not a convergent sequence. It gets neither indefinitely close to 1 nor indefinitely close to minus 1, because no matter how far you go in this sequence, you're always going to then flit backwards and forwards. So you can't say it gets and stays indefinitely close to 1, and you can't say it gets and stays indefinitely close to minus 1, because it doesn't. It flits back to the other one. So this is not a convergent sequence. However, it is a bounded sequence, and it contains a convergent subsequence, which is what the Bolzano-Weierstrass theorem is about. So you can take this subsequence where you get rid of all these terms now. So you get rid of this one, you get rid of this one, you get rid of this one, you get rid of all the minus 1 terms, and then you end up with a sequence that's just 1, 1, 1, 1, 1. And of course, that is a convergent sequence that converges to 1. So this is an example of the Bolzano-Weierstrass theorem, a really simple example of the Bolzano-Weierstrass theorem in action. It's saying that whenever a sequence is bounded, like this one, it will contain a subsequence that is convergent. In fact, this one contains two subsequences that are convergent. It contains this sequence, and it contains the sequence minus 1, minus 1, minus 1, minus 1, minus 1, minus 1, forevermore. In fact, it contains more than two, because you could have the sequence 1, 1, 1, and then you could have a minus 1 here, and then just the rest all being 1, and that still converges to 1. So there are loads of subsequences of this that converge. These are obviously the two most trivial examples, and you can see that all subsequences of this will either converge to 1 or they'll converge to minus 1. What this theorem is actually capturing is extremely deep and extremely interesting to think about, which is that if you have an infinite number of points within a finite interval within the real numbers, then they have to accumulate up somewhere. So in this example, this infinite sequence of real numbers, they are accumulating up at 1 and minus 1. So you've got an infinite accumulation up at the point 1 and an infinite accumulation up at the point minus 1. They can't just be spread out and not accumulating up anywhere. They have to accumulate up somewhere, is what this incredible theorem is saying. And that's actually an incredibly deep and interesting thing to think about. And that place where they're going to be accumulating up at is one of the limits that you will be able to find a subsequence of that's converging to that. So, for instance, we can find subsequences that converge to 1 where the points are accumulating up, and we can also find subsequences that converge to minus 1, which is another point where, for this sequence, the points are accumulating up. Now, this is a really boring example, but you can hopefully think of more interesting examples in your head and try to think what it looks like in the picture. Remember, this is the really deep part of this, that if you have an infinite sequence of points in a bounded interval of the real line, then they can't not accumulate somewhere. They have to accumulate somewhere. And that accumulation point is where you're going to be able to find a subsequence that converges to that limit that is that accumulation point. Just to develop the intuition here a bit more, Again, I've drawn a picture of the real line here, and we're now considering a bounded portion of the real line for the points of our sequence to be within, and the blue dots are representing points of the sequence. We've talked about how they must accumulate up at points. If the sequence is non-convergent, then what that means is it's going to be accumulating up at multiple different points, potentially more than two. This is showing really for two, but you could have 3, 4, 5, etc. And that's the reason it's not overall convergent, because it's really, if you like, converging to multiple different places, accumulating up in multiple different places. When the limit truly does exist, that's when it's accumulating only in one place. So to prove the Bolzano-Weierstrass theorem, we need to prove that what I'm showing you here pictorially really does happen, that the points of the sequence have to accumulate up somewhere. And the way we're going to do that is we're going to show that one of these accumulation points at the very least exists, and the one we're going to actually go for is the highest one. So if you imagine a bigger picture where there are maybe 5 accumulation points, we're going to find the topmost one, so the one that's highest up in the interval, and that has a special name. It's called the limit superior, for obvious reasons, because it's the one right at the top. So let's examine the notation and definition of this. So the limit superior, written lim_sup, of the sequence xn as n goes to infinity, the definition of this is going to be that it's the limit as n approaches infinity of the supremum of all the little xi's from I is greater than or equal to little n, where I is a natural number. So this is going to form a sequence, and let's just talk about what this sequence is going to be. So the first element of the sequence is going to be the supremum of the set that contains all the elements of your original sequence x. So every single element is going to be in there. Whatever the least upper bound of that is, that's the first element of the sequence. The next element of the sequence is the supremum of the same set bar the first term. After that, you get rid of the first and second term, and you start with the third term. So the fourth term of the sequence is then going to be the supremum where you start with the fourth term of your original sequence. So you're gradually taking the supremum of a smaller and smaller set as you take more and more of the terms out from your sequence x. The limit of this sequence as n approaches infinity, if that exists, is then what we call the limit superior of the original sequence as n approaches infinity. So this is a complicated definition, and I think the best way to improve your insight is to do some examples, and we're going to start off with non-interesting examples. So, of course, the main reason this definition was created is for the bounded example. It becomes interesting in the bounded example. However, it still applies for the non-bounded example. So let's take some non-bounded examples. So we'll take our trivial example, the sequence 1, 2, 3, 4, 5, 6, 7, 8, etc. If we then want to consider what is the lim_sup of this sequence, well, we need then the sequence of the suprema. So we start off with the supremum of all elements of the sequence. Well, that's not, it doesn't exist. There is no supremum. We could say it's infinite if you like. So we've got infinity there. And then the next one, we take out 1. Well, that doesn't help us at all. The supremum still doesn't exist. It's unbounded, this sequence. So it's infinity and onwards. It just goes infinity, 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 infinity. So it's a sequence of infinities, effectively. So if you like, you could say that the lim_sup of this sequence is infinity, but it doesn't mean anything. It's not a clever thing to say, because really the supremum doesn't exist. So it's not an interesting definition at all in this context where it's not bounded above. So we do not like this definition for sequences that are not bounded above. And remember, the intuitive thing that we're capturing here, and I'll explain to you how it intuitively captures that, is this highest, this top one of the accumulation points for our bounded sequence. Let's now do another example. So now we'll take the example where it's not bounded below. So we'll take the example -1, -2, -3, -4, -5, -6. If we consider what the supremum of the set of all the sequence is, well, that's going to be -1. It's the maximum point there. So it's -1 here. Then the supremum of all the points of the sequence bar the first one, well, that's then minus 2, because minus 2 is now the top point, so it's going to be minus 2, and so on. This one's then going to be minus 3, minus 4, so we get an exact copy of the same sequence. And then if we try and take the limit of that, well, of course, the limit of that doesn't exist. It's, if you like, negative infinity. So again, it's not an interesting definition at all. It's telling us, effectively, that this sequence that we're trying to find the highest accumulation point of doesn't actually have a highest accumulation point, which we know intuitively because this sequence isn't bounded below. And in this one, it's telling us that the sequence where we're trying to find the highest accumulation point of, again, it doesn't exist because it's unbounded above. It doesn't have a highest accumulation point. So this is an interesting definition in the context of it being bounded. So I think it might be helpful to remind ourselves of what we're trying to achieve. So we have a bounded sequence xn, and we want to prove that there exists a convergent subsequence for this, i.e. that the points of that sequence do accumulate somewhere within our interval. The way we're going to do that is, one, we're going to look at this thing that we've got here, and we're going to deduce that this always exists, this definition that we've just defined here, and we're going to show that this limit superior, is one of these accumulation points. It is in fact the topmost of the accumulation points within the interval, and therefore we will be able to find a subsequence of our original sequence xn that converges to the limit superior, and we'll have then done what we aim to do. We'll have shown that there is a convergent subsequence of our sequence xn. So part 1 then, we need to prove that the limit superior is always going to exist. So look at this definition. It's the limit of this sequence. This is a monotonically decreasing sequence because the sets that we're taking suprema of are progressively getting smaller. So the supremum of this set can only be less than or equal to the supremum of this set because this set is contained within this one. This one has one additional element. Following on, this set is this set minus this element. So the supremum of that can only be less than or equal to the supremum of this. So this sequence is just getting smaller. It's monotonically decreasing. Each term is less than or equal to the term before it. We also know that the sequence is going to be bounded below because if we relabel up each of the elements of this sequence as Sn, where Sn is the supremum of the set from xn onwards, we know that each one of those elements, Sn, is going to be at least greater than or equal to, well, it's going to be greater than or equal to all of the elements in here, but it's going to be certainly greater than or equal to the first of the elements in it. And we know that all the elements of the sequence x are greater than or equal to the lower bound, because we're assuming now that the sequence that we're dealing with is bounded, because we know that this only is interesting in the context of bounded sequences. So for all little n is an element of the natural numbers, it's true therefore that the elements of this sequence are going to be greater than that lower bound of the sequence x. So all of the elements of this monotonically decreasing sequence are greater than or equal to this lower bound, so indeed this is a monotonically decreasing sequence with a lower bound, and therefore it's going to have a limit within the real numbers. So when this is a bounded sequence, the limit superior, defined like so, is always going to exist. And the intuitive thing that you should see what this is meaning is it's this highest one of the accumulation points. And the reason that this definition in terms of suprema gives you that is because if you think about taking these progressive suprema where you're gradually taking out more and more of the terms, and you think about this highest one of these accumulation points, because this is an accumulation point, you know, there's a convergent subsequence of this sequence that's converging to that accumulation point. There's an infinite number of points accumulating there. So never in this sequence of suprema are you ever going to get past that, because no matter how long you go along in this sequence, you've only removed a finite number of elements, but there's an infinite number of elements accumulating there, so nowhere in this sequence are you ever going to be able to remove an infinite number of points that have accumulated at this highest one of those accumulation points. So you're never ever going to get beyond this accumulation point in this sequence of suprema, and therefore that's why the limit of this sequence of suprema is indeed going to be that highest one of the accumulation points. That's the intuition behind what we're doing here. Of course, what we still need to do is rigorously show that now that we know this thing exists, that there is indeed a convergent subsequence of the original sequence X that converges to that. And then we've shown that this intuitive picture that we have in the back of our head of these points accumulating here is true. So now that we've established that if the sequence X is bounded, lim_sup will always exist, let's now show that it's possible to construct a subsequence that is going to converge to lim_sup. So a new picture here. So here's the real line. The sequence X is going to be bounded with an upper bound BU and a lower bound BL. So we're only interested in this interval here. And we're going to reterm the lim_sup of our sequence, whatever it's equal to. We're going to call that L just because it's simpler. So we'll say L is here on our picture. Some more abbreviations that it's helpful to use. We're going to use SN to mean this sequence of the suprema. So lim_sup therefore is going to be the limit of this sequence of the suprema, and of course the sequence of the suprema is defined thus: Sn is the supremum of the set from Xn onwards. So we want to show that it's possible to construct this subsequence. So the way we're going to do this is by considering progressively smaller intervals around the point L. So we'll start off with epsilon is equal to 1. So I've drawn this on in white here. So imagine up here that this is L plus 1, and down here this is L minus 1. What we want to do to find the first term of our subsequence is find an element that is within this interval of epsilon size 1. How can we prove that such a term exists? Well, go back to the definition of what L was equal to. It's the limit of this sequence of suprema. So by this definition, there must be a point in this sequence of suprema where you get into this one interval and stay within this one interval. So we'll say that this point of this sequence, this term of this sequence, S little n, that this represents a term in this sequence which is within this one interval. So it's here. Because of course it's going to be greater than or equal to L, so it's not going to be on this side of L, it's going to be on this side of L. Now, go back to what the definition of Sn is equal to. It's the supremum of this set Xn onwards. If you then consider Sn minus 1, so you consider effectively the one interval around Sn, so imagine that this red line here represents Sn minus 1, there must exist a point in this set that is within that interval between here and here, which obviously is contained within the one interval around L. The reason for that is that if there isn't a point in there, then this point down here could be an upper bound of this set, contradicting this being a lower bound. So if this is not an upper bound, there must exist a point in this set that is here, and this cannot be an upper bound, otherwise this wouldn't be the least upper bound of this set. So that proves that there must be a point in this set that is in there, and therefore is in this one interval around L. So you can take that point from the original sequence, and you can let that be the first element of our subsequence that we're picking. For the sake of example, let's say that that term of the sequence that ended up being picked was x42. Let's now think about how we would construct the next term of the subsequence. So now we're going to halve the epsilon size. We're going to go to epsilon is equal to a half. So imagine halving the epsilon size on the picture. For the exact same arguments as previously, you will be able to find a term of the sequence that is within that epsilon interval. The thing is, you want to make sure that the next term that you find inside that new interval is going to be further along in the sequence, so it can't be x20, for instance. So how are you going to do that? Let's think about it. So if we have this epsilon equals a half interval, and I might just draw a picture of this. So I've drawn this on the picture here. So here again we have L in the center in white, and this is now our epsilon is equal to a half interval. So again, because of the definition of this, you can find a point in this sequence of suprema where it's within this half interval and all the terms after it are within that half interval. Now, we'll call that again Sn. This time, you are not just going to take the first Sn you meet, the first one that satisfies being in the half interval and all other terms afterwards are in the half interval. Instead, you're going to make sure that it's also greater than this number you've got already, because if by doing this you're ensuring that the next term that you're going to pick to be in the subsequence is going to be further along in the sequence than this term. So you want to find a point in this sequence of suprema that's inside this half interval, and you want to make sure it's greater than 42, but you can always do that because, of course, there's going to be a point in this sequence that is in here, and then all subsequent terms are in there. So you can just go along those subsequent terms until you reach one that's greater than 42. Then, for the exact same argument we used previously, consider the half interval around this. So consider this supremum, take away a half, consider that little interval that's inside our interval around L, and then find a term in the original sequence X that's inside there, which you can do because of the definition of this as supremum, and therefore there has to be something inside that set that is within this interval, otherwise this Sn minus a half would be an upper bound. So you can then find that term, and you'll then put that along here as your next term in the subsequence. And for the sake of example, we'll say that this next term in the subsequence was x100, so in blue again here. And you continue on in this fashion. Next, you'll make epsilon equal to a quarter, and then you'll make epsilon equal to an eighth. You'll half each time so that you're getting progressively smaller and smaller intervals, and you'll get more and more terms in this subsequence. And you have then got a subsequence of the sequence x that gets and stays indefinitely close to L, and therefore converges to L. So overall, what we have done is we've shown that for any bounded sequence x, the limit superior always exists, and moreover, there exists a subsequence of our sequence x that converges to the limit superior. And we've discussed already how intuitively what this thing means is the greatest of these points where the points of the sequence are accumulating at. We have therefore actually proven the Bolzano-Weierstrass theorem, because the Bolzano-Weierstrass theorem is that for any bounded sequence there exists a convergent subsequence. So this subsequence that converges to the limit superior, that is a subsequence that is convergent. Therefore, as this exists for any bounded sequence, we've proven that any bounded sequence will have a subsequence, at least one subsequence, that does converge to a limit. Indeed, we've found it. It's this subsequence that converges to the limit superior. We now want to proceed to discuss how we can use the Bolzano-Weierstrass theorem to conclude that all Cauchy sequences converge to a limit within the real numbers. But just before we do that, I'd just like to say a little bit about a related topic to the limit superior, which is the limit inferior. So limit inferior, or lim_inf, is a very related topic to lim_sup, and it's an interesting topic for bounded sequences. So again, we'll assume this sequence is bounded. If it's not bounded, just like lim_sup was pretty unspecial, lim_inf is also going to be not particularly interesting. So we'll assume the sequence is bounded, then the limit inferior, or lim_inf, is similarly defined as the limit as n approaches infinity of a sequence that is made of infima, so the infima of the set of all elements of the original sequence from I is n onwards. So the first term is the infimum of the set of all elements of the sequence. The next term is the infimum of all elements of the sequence apart from the first term, and then the third one is minus the first and the second. The fourth one is then minus the second, the third, and the fourth. The first, the second, and the third. So that the first element in the set is the fourth term of the sequence. And This is going to be a monotonically increasing sequence because you're taking infima of progressively smaller sets, so it can only get bigger. Again, it's going to be bounded above if the sequence is bounded, because each one of these is going to be smaller than the first element in the set at the very least, and each one of those elements is smaller than the upper bound of the entire sequence. So every one of the infima is going to be bounded by the upper bound of our original sequence. So this sequence is going to be a monotonically increasing sequence that is bounded above. Therefore, it does exist, provided that the original sequence was a bounded sequence, and that's what is meant by the limit inferior. And intuitively, what this means is the smallest one of the accumulation points. So as we've discussed previously, for a bounded sequence, the infinite number of points in that sequence has to accumulate in a number of points, at least one point somewhere within our finite interval. We've proven that. That's what the Bolzano-Weierstrass theorem says, that it must accumulate somewhere. There must be a convergent subsequence. Indeed, for some sequences, it's going to accumulate rather in more than one place. So we might have the scenario like in this picture where you've got two places where it accumulates, but you might have even more. You might have four, for instance. Lim sup, as we've agreed, as we've discussed, is then the answer to where the points are accumulating, the greatest one of these points where they're accumulating. Lim inf is then going to be the smallest one, the smallest point where they're accumulating, so it would be this one down here. And the reason for that is that this sequence of infima, because there's an infinite number of points accumulating at this smallest accumulation point, the infima are never going to be able to get beyond that accumulation point, that lowest accumulation point, because every single one of these infima has only taken away a finite number of elements from the set, and there's an infinite number of elements or points of the sequence accumulating here. So you're never going to be able to remove all of them, so always the infimum is going to be trapped by this lowest accumulation point, and indeed as you go progressively on, the infimum is just going to get closer and closer and closer to it, so that the limit, what it's approaching, is going to be that smallest accumulation point. So similarly, you could make the same argument as we've just made for the limit superior about how there must exist a convergent subsequence. You can make that same argument for lim inf. So you could have proven the whole of the Bolzano-Weierstrass theorem using lim inf just as well as you could for lim sup. And also, if the sequence is convergent, if there is only one accumulation point for the bounded sequence, then lim sup and lim inf are going to equal one another, and they're going to equal the limit of the sequence. So now back to Cauchy sequences. So we're going to use the Bolzano-Weierstrass theorem to show that all Cauchy sequences must converge in the real numbers. So here again is the definition of a Cauchy sequence. Now, hopefully it's clear to you that if a sequence is Cauchy, it's going to be bounded. So it's going to be bounded above and bounded below. Just in case it isn't, let me make that clear. So this places huge restrictions on the sequence. Quite simply, set epsilon equal to 1, and if it's a Cauchy sequence, it must be the case that there exists some big N in the natural numbers. There exists a point in the sequence where, for all the points beyond that in the sequence, if you take the difference between them, it has to be less than 1. So it might be the case that big N is equal to 100. Let's just, for the sake of a concrete example, say big N is equal to 100 for epsilon is equal to 1. Then if you take any little n such that it's beyond 100, so little n could be x200 for instance, or x1000 or x101, for absolutely every single one of the points of the sequence beyond x is equal to 100, if you take the difference, the modulus of the difference between x100 and that, it has to equal less than 1, i.e. all the points in the sequence beyond x100 are no further away from it than 1. They're in the interval x100 plus 1, x100 minus 1 to x100 plus 1. So that's clearly a bounded set. And then all the points in the sequence before that, so x1 all the way up to x99, that's a finite set, that's clearly bounded. So when you union those two together, this set with all the other points in the sequence, x100 onwards, it clearly is going to also be bounded. So all Cauchy sequences are bounded, and therefore we can apply the Bolzano-Weierstrass theorem to them. So let's do this now. So this is our Cauchy sequence here. So we know that the terms of this sequence get and stay indefinitely close to one another. Because it's bounded, we can now apply the Bolzano-Weierstrass theorem, which says that there must exist a convergent subsequence of this sequence. So let's say here, this is our subsequence, and this is converging to some limit L. What we want to now prove is that the whole sequence must also converge to that limit L. And intuitively, the reason this is true is for this to converge to the limit L, it has to get and stay indefinitely close to L. At the same time, this entire sequence is getting and staying indefinitely close to one another. So as these points are getting indefinitely close to here, these other points that we've omitted, got rid of to create the smaller subsequence, they're all getting indefinitely close to the terms of this subsequence, and that's the reason why this overall forces the whole sequence to be converging to the limit L. Rigorously, let's just go through this. So here is our limit L on the real line, and we want to prove that for any epsilon, so we've drawn our epsilon interval here, so here's L plus epsilon, here's L minus epsilon, we want to prove that we can find a point in this sequence where all of the terms after it are inside that epsilon interval around L. To do this, consider epsilon over 2. Consider this interval, this smaller interval here, where this is L plus epsilon over 2, and this is L minus epsilon over 2. Because we know this sequence converges to L, we can find a point in this sequence where it and all the terms after it are inside there. Because this sequence is Cauchy, we can find a point in this sequence where it and where from that point onwards all the terms are less than epsilon over 2 in distance away from one another. So I've added that onto the picture here. So this blue line here is supposed to represent the point in this sequence after which, if you take any 2 points and ask how far away are they, it's going to be less than epsilon over 2. So just to give a concrete example, it might be x200. And if you take xm and xn, where m and n are greater than 200, the distance, or the amount by which they are apart, is going to be less than epsilon over 2. Now, in red here, this represents the point in our subsequence where it and all points after it are within the epsilon over 2 interval around L. Now, if this, to give a concrete example, might be x100. x100 might be the point in this subsequence where it and all points after it are inside that epsilon over 2 ball. What you would then want to do is go on, because you want it to be, you want to use a term in this subsequence that is beyond this threshold, beyond this term in the Cauchy sequence. So you'd continue going along the subsequence. This is too low. x100 is below x200. So you'd continue going below, you'd continue going on until you got to a term in the subsequence that was beyond x200. Now, x200 might not actually be in the subsequence, but there will be some term following it. So that might be x209, for instance. Let's say that is in the subsequence, and that's the first term that's beyond x200. So x209 now is going to be in this epsilon over 2 interval around L. And what you can also say is that now all of these terms from x200 onwards are going to be in this epsilon over 2 interval around x209, because x209 is going to obey this criteria here, that its distance from any other term that is beyond x200 has to be less than epsilon over 2. So they all are going to be in that epsilon over 2 interval around x209, and that in turn is going to be contained within the larger epsilon interval around L. So I have basically found you a point in this sequence here where it and all terms beyond it are within this epsilon interval around L, and I can do that for any epsilon. Hence, I've shown that this sequence must converge to the limit L. Overall, the argument consists of if this subsequence gets and stays indefinitely close to L, and this overall sequence gets and stays indefinitely close to each other, the terms of that sequence, then of course it's overall, the whole thing has overall got to converge to L. So overall, we have proven then that all Cauchy sequences are going to converge to a limit within the real numbers. And the way that we remember did that is using the Bolzano-Weierstrass theorem, which relied upon the existence of lim_sup and lim_inf, and their existence relied upon the theorems about monotonically increasing and monotonically decreasing sequences that are bounded above and below respectively, which required the least upper bound property. So that's where ultimately that property of the real numbers came in. And remember, we begun this video by giving an example of a Cauchy sequence of rational numbers which doesn't converge because even though the terms are getting indefinitely close to one another, it's converging to one of the holes in the rational numbers. So fundamentally, in order for all Cauchy sequences to converge, there must be no holes, which is what the least upper bound property captures. So we'll end the video there. Thank you for watching.